Hello, everyone. Mr. Minnick's my name. Math is my game. I've been misspeaking all day long, so hopefully that doesn't follow suit in this video today. We're looking at Chapter 6, Section 2, multiplying and dividing radical expressions. The Common Core content standard for this lesson, you don't need to write that down. It's ASS E2. Algebra, seeing structure and expressions. You're supposed to be able to use the structure of an expression to identify ways to rewrite it. That actually makes a lot of sense in the context of the lesson. If you were here on Monday and on Tuesday, in 6.1, basically what happened is it was sunny in 70 in Newton Falls. And if you missed that, I'll recap that one more time. What that means is we were simplifying something like the square root of 25 x squared y to the 6th. And when I say it's sunny and 70 in Newton Falls, what I mean is everybody goes out and plays basketball. What I mean by that is everything under the radical, like this 25, is not going to be under the radical anymore. So what if we simplify that, what comes out from the rad 25? A 5. So we can rewrite this as 5 times something. If we look at the x squared and we think to ourselves, what's the square root of x squared? What is it? X, good. And if we finally look at this y to the 6th and we take its square root, it's y to the 6th divided by 2, or y to the 3rd, or y cubed. Cool. Now you guys know I like Chinese food, and the best Chinese food comes from the Main Moon in Newton Falls. And you order and you say, yeah, I'd like some crab rangoon and some General Tso's and pork fried rice, $2.50 more. I know, it's $2.50 extra, I know. And they say, anything else? And the anything else, does anybody know the anything else on this? Not plus or minus, absolute value on the x and the y cubed, yeah. Because of the even odd rule. So if you missed Monday's lesson, check it out online. And if you have any questions about it, I'll gladly answer them. So that was 70 and sunny. What's going to happen today? What's going to happen today in this 6.2? It's not going to be sunny. It's going to be partly cloudy. It's going to be partly cloudy and 70. What I mean by partly cloudy and 70 is we're going to be simplifying something like this. The square root of 8 x cubed y to the 7th, maybe, something like that. Now, when it's partly cloudy and 70 in Newton Falls, there's still diehard basketball players who are going to be out balling. Similarly, with this expression, there's going to be some things that go outside and play. And when I say that, what I'm saying is there's going to be some things that are going to not be under the radical when we simplify this. And there's going to be other things, like me, that stay inside and watch Springer sitting on the couch eating some white cheddar popcorn. That was a little too specific. So anyway, this ASS E2, they want us to be able to rewrite things. So the deal is we got to be able to think of this 8 in terms of its factors, one of which is a perfect square, the biggest perfect square factor of 8, which is what? 4. So we're going to rewrite that 8 as 4 times 2. And then x cubed isn't a perfect square, but we could break it down the Long Beach way. We could kind of rewrite x cubed as x squared times x. You picking up what I'm putting down here? Now, you don't have to do this, but I think it makes it a little bit easier to keep them separated, to organize it, that kind of thing. So who could read my mind and tell me how I'm going to rewrite y to the 7th? What are you thinking? You could do y to the 4th and y to the 3rd, but then that y to the 3rd would end up needing to be broken down a little further. What do you think? Yeah. Or you could go y squared, y squared, y squared, y. Take your pick. If you want y squared, y squared, y squared, y, a y is going to pop out, a y is going to pop out, and a y is going to pop out. So what pops out? A y cubed, right? So take your pick, y to the 6th y, or y squared, y squared, y squared, y. Which one do we want? Y to the 6 times y? Okay, all right. Cool beans. So just like we did before now, we're going to look at this and we're going to say, well, the square root of 4 we know is what? 2. So a 2 goes outside and plays basketball. So that eliminates that 4 from this expression now. Let's move along to something else that's going to go outside and play basketball. Because of this x squared, what's going to go outside and play basketball? An x to the first power, right? So that takes care of this one. Let's move on. What else is going to go out and play basketball? A y cubed. Good. So a y cubed also goes out and plays basketball. So we got those things done. Here's the square root. Here's everything that's inside on the couch with the white cheddar popcorn watching Springer. What is it? 2xy. And you know I like Chinese. Absolute value on the x and the y cubed that are not under the radical. What do you think? Not bad? So what's going to make this more difficult is chapter 6, section 1. The title wasn't square roots. It was square roots and other roots, right? So if you missed 6.1, we said it's probably a good idea to know your first 20 perfect cubes, or perfect squares. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 1 something. You said it. 196, 225, 256. That gets us up to 16. And then what? Boy, we got awful quiet there from 289. Good. And 324 and 361 and 400. Good. So those are the first perfect 20 perfect squares. It's handy to know those. It's also handy to know the first 10 perfect cubes. 1, 8, 27, 64, 125, 216, 343, 512, 729, and 1,000. All right. So I'm not telling you to memorize these to ruin your life. I'm not telling you to memorize these because I want you to memorize things. I'm telling you to memorize these or have these handy because you're going to need to know them to be able to simplify these things. Perfect fourths. I think we went to the first 5, right? So 1, 16, 81, 256, awesome, and 625. I don't know if you know this about perfect fourths, but fourth rooting something, I know that's really not a verb to fourth root something, but taking something's fourth root is the same thing as taking its square root and taking its square root. So if you think about 81, what's the square root of 81? 9, and the square root of 9? 3. So 3 is the fourth root of 81. Okay, so, all right, finally, then the perfect fifths. The first 3 perfect fifths, I think I said you should probably know, and they're 1, 32, and 243. Good. So being able to refer to these is probably going to be something that you're going to need to be able to do. So in this section, I don't know why I think of these weird things, but has anybody ever taken their finger and taken their other finger and put them toward each other about 6 inches in front of their face? You ever do that? Maybe 3 inches in front of your face. Do you see what happens? Do you see what happens? Anybody see it? They touch before they touched. A third finger shows up in the middle, right? Do you see that? So I don't know why that happens, but a third finger ends up showing up in the middle. Looks like a sausage, right? When you go like that. That's kind of the way I think about doing something like this. We're going to be simplifying. We're going to be simplifying something like the square root of 3 x squared y to the x squared y to the 5th times the square root of maybe something like 27 x to the 3rd y to the 7th. We're going to be simplifying something like that. Now, I don't know if you're aware of this or not, but back in chapter 4, there was this property of radicals that says the square root of AB is the square root of A times the square root of B. That's a definition, and definitions are true in both directions because they're biconditional statements. In geometry, you learn that, right? Remember that? Okay. So the deal is, I can say that the square root of something times the square root of something is the square root of the product of those two radicands. In other words, I could say that this ends up being the square root of, what's 3 times 27? 81. And then what's x squared times x cubed? X squared times x cubed, your rule of exponents, that's going to be x to the 5th. And then lastly, y to the 5th times y to the 7th is going to be, is it y to the 12th? Cool. Okay, y to the 12th. All right. So now we got to simplify that. Do we know the square root of 81? It's going to be 9. So a 9 pops out. The 81's done. Now that x to the 5th, is all of that going to go out and play? No. If we think about that, that x to the 5th could be thought of as x to the 4th times x to the 1st. So what's going to go out and play from the x's? X to the 4th square root. So x squared goes out. So we're done with that part of it now, right? All right. And what else goes out and plays? Y to the 6th. Cool. And that y to the 6th takes care of all of the y, right? So what's left watching Springer? Just an x. Do we need absolute values on this one? No. And the reason we don't is because those powers, those exponents, those degrees of these terms are even. So that's the kind of direction we're going to be heading. Okay? So that rule can be extended to nth roots. So what I'm trying to tell you is this. In general, the nth root of A times the nth root of B could be thought of as the nth root of AB. So that not only works for square roots, it works for any kind of root as long as, notice how this is an n, and this is an n, and this is an n, right? Does anybody remember what that number in the notch is called? The index. As long as those indexes, or indices as the right way to pluralize that, as long as the indices are the same, you can do that. So what I want to be real clear of is if you have the nth root of A, and you're multiplying that by the mth root of B, it's not possible to combine those. Okay, we can't do this and say, okay, well maybe we average the two. Maybe we subtract the two. Maybe we divide the two, and it's A times B, and it's the somethingth root at the n times n. No, we can't do that. There's really nothing we can do to that. Okay, so here we would just say cannot simplify. And the reason we can't is because the indexes, because the indices differ, because they're not the same. Okay? Because those indices, the n and the m there, because they're not the same number, it's not possible to simplify that. So far, so good. These rules also apply to fractions. Same goes for fractions. So in other words, the nth root of A divided by the nth root of B is the nth root of the fraction A over B. And that statement, because it's a definition, because it's a biconditional statement, can go both ways. We can go either direction with that. It's not just one direction. And yes, I went there. I said one direction. I hope some of you had a chance last night to watch the Elton John special on that one TV channel, CBS. It was awesome. Lady Gaga singing Elton John to Elton John. Good times. Good times. All right. So let's see what examples the authors of your textbook have put together. By the way, I know it's the 4th 9 weeks. I know it's kind of late in the year, but if anybody ever wants a copy of the textbook, I have like a few copies of it. Look, the book just said the same thing I just said. So In problem 1 here, they're asking us for number A. Can you simplify the product of the radical expression in problem 1, part A? No, why not? Because the indices are not the same. No, because the indices are not the same. I don't know why, but I want to mix together Spanish and German right now. What is it with Germans? Why do they always sound so mad? Instead of saying no, what do they say in German? Nine! And you got to be mad when you say it. Nine! Because the indices are not, in Spanish, how do you say the same? El mismo. 9! Because the indices are not el mismo. Muy bien. All right. Let's look at part B then. Could we simplify that? We could, and we're going to have to do that finger thing 3 inches in front of you, 3 inches in front of your face. So if we do that, if we do this thing, what I'm saying is we're going to have the third root of -4 times 2, which is the third root of what? -8. Now, is it possible to take the 3rd, 5th, 7th, 9th odd indexed root of a negative number? It is. So we're asking ourselves, what number times itself a third time equals -8? And it's got to be -2, right? So whoop, there it is, -2. We can combine those because the indices are the same. So if we simplify it, it's the third root of -4 times 2. Third root of -8, and the answer is -2. How do we feel about that one? Okay? The one thing that I got to admit about math, it's probably one of the subjects that you'll use the least in the real world, but it trains your brain the most to problem solve. I love when people ask that question, when are we going to use this in the real world? Never. But ask this question, when are you going to need to know what a split infinitive is in the real world? Exactly. A split infinitive, it's where you use an adverb in the wrong place in a sentence. Like I gladly walked instead of I walked gladly. Something like that. I did pretty good on the ACT in the English part, second time around. Reading, don't ask me. I'm not a reader. All right, let's look at the Göttingen just to make sure we do Göttingen. Göttingen part 1, Göttingen number 1, part A, can we do that? No, because the indices are different, right? What about part B? And it's going to be the 5th root of what? 10. Now let's think about that. Does 10 have any factors that are perfect fifths other than 1? No, it doesn't. So the deal is we can simplify it to that, and that's the best we could do. Make sense? All right. Cool. Cool beans. So let's try problem 2 here. Ooh, now we're into third roots. Oh, man. It'd be handy if we knew some perfect cubes, like 1 and 8 and 27 and 64. Now, 54 is not any bigger than any of those. So let's ask ourselves, can we rewrite 54 using one of those factors? Why not? It's 54 is really what times what? It's 2 times 27, right? So, and who can read my mind and tell me how I'm going to rewrite the x to the 5th? X to the 3rd times x squared, right? Cool. So, again, it's 70 and partly cloudy in Newton Falls. So, cube root of 27 is 3, so a 3 goes out to play. 27's done. We'll forget about the 2. We can't do anything with it, so it's going to be on the couch with the white cheddar popcorn watching Springer. Actually, Springer's over now. It's going to be watching, what comes on after Springer? What is it? Okay, well, probably one of those judge shows. Yeah. All right. What about the third root of x cubed? An x pops out. Good. So that takes care of that. So inside on the couch, watching one of those judge shows is going to be what? A 2 and an x and a squared. Now somebody's looking at that and they're thinking, x squared. I have to be able to do something with that. No, you don't. Its power is 2. The radical's index is 3. You can't do anything else with it. So the answer here is 3x times the third root of 2x squared. One word of caution, one caveat, one thing to look out for right here. See if that works the way it's supposed to. The index, be careful where you write your index of 3. We got a question? Okay. No, go ahead. Go ahead. Yeah. Isn't 3 divided by 3 1? Yeah. So yeah, this 3 here divided by this 3 is 1, and this power out here is 1. Yeah, that power is 1. Yep. Good question. Good question. Yeah, and so that's kind of where I was going with this. The deal is, it almost looks like I have a 3x cubed out there, right? It almost looks like I have a 3x cubed out there, but I don't have a 3x cubed. That 3 right here, let me get my magic pen out. That 3 right there is the index. Okay, so you got to be careful how you write that whenever you craft your answer. I know that's weird to say, I'm crafting my answer, but whenever you write your answer, some of these get confusing, and so tomorrow when we're going over the homework, you might have the right answer and you're just going to read it wrong because you can't tell if your power is an exponent or an index. Does that make sense? Cool. Good. All right. Well, we got our little list of perfect cubes. Let's see if that'll help us on the Goding. Does that help us on the Goding? Can we rewrite 128? It's what? 64 times 2. How are we going to rewrite the x to the 7th? X to the... So our index here is 3, so x to the 6th times x, right? All right, so 64 is cubed root. What is it? It's not 3. Good try, though. 64's cube root is 4. So 4 goes out to play. What's x to the 6's cube root? X squared. So an x squared goes outside to play basketball. And what's on the couch watching the judge show? 2x. They're probably making a chocolate milk, too, because chocolate milk with white cheddar popcorn is really good. Washes the kernels out. I have weird tastes in food, in case you didn't know. Recipe day? Yeah, I make a pretty mean mocha. All right. One of these days we'll have to try to have a food day. All right, so problem number 3. I got to be frank with you. Sometimes it's better to do that fingers 2 inches in front of your face thing. Sometimes it's better to do that, and sometimes it's better not to do that. What I'm saying is, if we look at the 72, if we go ahead and multiply 72 by 10, that might or might not make things more easy or more difficult for us, because 72 times 10 is going to be 720, right? That's a big number. Now we're going to have really big factors to find. But when I simplify radicals, I like to find the biggest perfect square factor I can of the radicand of that number. What's going to happen with my x's? I'm going to end up with x to what power? X to the 4th. Good. That's nice because it's 70 and sunny with that. How many, what's my y's going to be? It's going to be y to the what? Y to the 5th. Should I write it as y to the 5th or should I rewrite it? Y to the 4th times y. Knowing that this is really a y to the 5th, but knowing I'm going to have to simplify it later, right? Good. Everybody know where I got the 720 from? Okay, awesome. So I know sometimes we get lazy as Americans because it never ceases to amaze me. Somebody says, oh yeah, I know who wrote The Grapes of Wrath. Let me just look it up on Google. Think about that. I know who wrote the Books of Wrath. Let me just look it up on Google. Do you really know who wrote the Books of Wrath if you have to look it up on Google? Can you simplify the square root of 720 if you have to find its factors on Mathway? No. So anyway, don't be lazy when it comes to finding factors. You're going to find a good one real quick. 1 in 720. 1's a perfect square, but there's bigger ones than that. 2 and 360. Now, if we look at 360, we're thinking, hey, 36 and 10. But 10's got, well, wait a minute, we could do 36 is a perfect square, but 360 is not. Dang it. So a number is divisible by 3 if the sum of its digits, 7 plus 2 plus 0 is 9. 9 is divisible by 3, so 3 goes into this. In case you didn't know, it's 240 times, but that doesn't help because 240 is not a perfect square either. 4 and 180, nice. Now, 4 is a perfect square, but it's not the biggest one because we already know 36 is a factor, right? Here's the thing. You're starting to get frustrated. You're like, dude, you said you'd find one quick. I'm not lying. You're going to find one quick. Just be patient. A number is divisible by 5 if it ends in 0 or 5. There's 1, there's a 5, there's a 2 and a 2. 5 times 4 is 20. Oh my gosh, 144? That's the biggest perfect square factor. There it is. I told you it wouldn't take long, right? That's 144 and what? 5. Okay. All right. So we know then that this 720 is really 144 times 5. So what's going out to play? 12's going out to play basketball. What else? X squared, because that's the square root of x to the 4th. What else? Y squared, because that's the square root of y to the 4th. Good. And then playing on the couch with its sitting on the couch with its chocolate milk and its white. Now they got ding dongs. Hostess ding dongs are where it's at. I like ho-hos. Twinkies, I'm not a fan. Not even the chocolate ones. Those are gross. And if you like Twinkies, I'm sorry, but the ding dongs, that's where it's at. So what's got the ding dongs on the couch with the chocolate milk? A 5 and a Y. How do you feel about these? It seems pretty scary when you look at them. But if you break it down the Long Beach way and you do the finger thing, it's really not that bad. All right. Where these get to be nasty is when you get into fractions. Something that's going to come up, I don't know if any of you are taking pre-calculus next year. If you do, you're going to study the unit. Oh, we studied the unit circle. If you take applied math, we're going to study trigonometry and the unit circle. And there's this one instance that brings up 1 over the square root of 2. And I don't know if you know this or not, but that's bad. That is bad. To have a radical in the denominator is horrible. You're not allowed to do that in math class. It's 0.707, I think. Or rad 2 is 1.4414. Right, good. But the deal is with this, what we have to do, it ends up being rad 2 over 2, which is approximated by the decimal 0.707. But the deal is we have to do some magical stuff here. Abracadabra, alakazam. Please get rid of the radical 2 in the denominator. Ma'am. Question. Yes, that's exactly what you do. Yeah, you got to multiply by radical 2 in the denominator, which is going to make the denominator rad 2 times 2, which is going to make the denominator rad 4, which is going to make the denominator just 2. And whenever we take some kind of expression and multiply that expression by something, if we don't multiply it by anything other than 1, we're changing its value. So we got to multiply it by 1. So what do we got to do in the numerator? Have that rad 2 also, right? Cool. And 1 times rad 2 is just rad 2. And there it is. So there is a shortcut to the easy versions of these. And I might have showed you this at one point. Suppose we had 3 over rad 7. The shortcut way to think about this is whatever's in the denominator, the whole thing in the denominator is going to join the numerator. So we have a 3, we're going to have a rad 7. And what takes the place of the denominator then is going to be the radicand, which is just 7. Good. So if we had something like 8 over rad 2, if we follow that shortcut method, that's going to become what? 8 radical 2 over 2. And then we can cross cancel this 8 with this 2, so that's going to simplify one more time, right? To 4 rad 2. Cool. Good. So where these things get nasty is when we start throwing variables in the mix. Oh, man. So what about something like this? 7 over the square root of 8x cubed. Oh, man. Oh, man. 8's not a perfect square, is it? We need to transform 8 into the smallest perfect square that we can. Let's see, 1, 4, 9, 16. Hey, 16, right? So that's our target for the 8. So we're going to have to multiply by something over something, the same thing over the same thing. And it's got to be a radical and a radical, right? So a 2 to make that 8 into a 16, right? And x cubed, unfortunately, is not a perfect square. But if we multiplied x cubed by x to the first power, it's going to make that whole thing x to the fourth power. So let's go ahead and look at it, because you know that's what they say. Sometimes you just got to look at it. What's going to happen in our numerator? What's that going to be? 7 rad 2x. The denominator, if I think about the denominator maybe off to the side, the denominator is going to be, what, the square root of 16x to the fourth, right? So what is the square root of 16? 4. And then square root of x to the fourth is x squared. Good. And that's it. That's the kind of thing we're going to be doing with these. Okay? What do you think? Make a little bit of sense? Good. You don't want to see what's happening next week. In our 2-hour class next week. All right. So I really wish that the finger trick, I really wish that you could somehow do that in a vertical fashion, but it doesn't work that way just because of the way our eyes are. Okay? You could cross an eye and make it work. Okay. But sometimes we want to go ahead and we want to put these things together across the fraction bar, and we can do that, and we can be picky and choosy about it. And I'm going to give a shout out to Clint Kindlesperker for being so awesome today. And I'm going to give a shout out to a 9th grader. Yes, I said it. I'm giving a shout out to a freshman, the prophet Isaiah Consolo. Anybody know him? I don't know what mask he had, but okay. Anyway, if you want to figure out how to do this the really efficient way, have a chat with Isaiah. He'll explain it to you. He really gets this. Okay. 18 divided by 2, what's that going to be? 9. So we can divide across that fraction bar because of those properties, right? So we're going to end up really with the square root of 9. And then similarly, x to the 5th divided by x to the 3rd. Do you remember your exponent rules? X to the 5th divided by x to the 3rd is x to the 5 minus 3, or x squared. Hey, it's 70 and sunny in Newton Falls. Everybody's playing basketball in this one. What do we get? 3x. I like Chinese food. Absolute value on the x, because that original index was even, because the power on that x is odd, and the even, odd rule. If you don't have the absolute value on these, not the end of the world, but we should kind of be cognizant of the fact that we need it on this one. Okay. All right, let's see if we can do that on number B. 162 divided by 3. That's what, 50-something? Is that 54? So this ends up being the 3rd root of 54. Wait a minute, 54 is not a perfect cube, but we had one like this earlier. We could rewrite 54 as what? 27 times, good, times 2. Okay. And then what about my y's? It's going to be y what? Y to the 3rd. So let's see who goes out and plays basketball. The 3rd root of 27? 3's outside playing basketball. 3rd root of y cubed? Y's out playing basketball. What's on the couch finishing up its ding-dong, about to wipe its hands off? And they're going to wipe their hands off just on the couch. That's disgusting. Why do you do that? Use a napkin. You filthy animal. Wiping off the ding-dong wax on the couch. What's the matter with people? Unless they clean the couch later that day. All right. Oh, man. This is it. This is the last one for the day. Wow. I have no clue where to start. 5/12 doesn't simplify, does it? Bob Saget. X up top doesn't have any X's in the bottom, does it? Dang it. Y squared in the bottom doesn't have anything in the top, and Z in the bottom doesn't have anything in the top. What I'm going to do is I'm going to keep them separated. Sometimes you got to keep them separated. So I've got a cube root up top of 5x squared, and in the bottom I've got a cube root of 12y squared z. Now I got to think to myself, I know 1 is a perfect cube. I know 8 is a perfect cube, and I know 27 is, and I know 64 is. And I'm trying to find a perfect cube that's going to match up with 12. 125. 216, I think, is going to be the first one. So how many times does 12 go into 216? That's once. That's once I said. That's 12. That's 9. That's 6. It's going to be 18. It's going to be 18. 12 times 18 is going to be 216. Okay? So the deal is, I'm going to have to multiply by something over something. It's going to be a third root over a third root. 12 times 18 is going to give me a 216. Y squared's not a perfect cube, but if I multiply by y, that'll take care of that. And z is not a perfect cube, so I'm going to have to multiply by z squared over z squared. So let's see what's going to happen here then. My numerator, I'm going to have 5 times 18, which is that 90? So up top I'm going to have a 90, x squared, y, z squared, under third root up top. In the bottom I'm going to have 216, and we said 216's cube root is what? 216's cube root is 6. In the bottom we're going to have y cubed, so y cubed's cube root is y. And we're also going to have a cube root of z cubed, which is z. Now, before we go ahead and say that the answer is A, we got to think to ourselves, does 90 break down any further? Does 90 have any perfect cube factors in it bigger than 1? 8 doesn't go into 90, does it? No. 27 doesn't. So that's all the further we can go with this. So the right answer here is what the Fonz says. A. Do you guys know the Fonz? Henry Winkler, Happy Days? Hey, doesn't he always say that? Well, I think that's it. Are there any questions, comments, concerns, short debates, long debates, shout outs? Nope. Shout out to the aliens who are coming on the 18th. That's next week. Preppers, I don't need to say anything to you. You're already ready. Have a great day. See you. Good.